So you folks will be my YouTube video. Woohoo! The work energy theorem. Work is measured in joules. Energy is measured in joules. This is how we're going to link together the reason why. I'm teaching you what I think is a cleaner version of the work energy theorem. If you take physics, upper level physics, you may see some textbook write, I think, a more simplified version. Jordan, is called the attention span. I need you here. So, you ready? Here we go. Energy is the ability to do what? This was our definition of energy. Who remembers that? Energy was the ability to do something. Work. That's why energy is measured in joules. And what we're going to try and do today is link energy and work. Now, our first definition of work, don't write this down, was the easiest but the least useful. It was force times distance. Don't write that down. It only worked, no pun intended, when the force was constant and the force and the distance were in the same direction. It was okay. The second definition of work that I gave you that day was, I said it was the area underneath a force versus distance graph. In fact, I recommended that you write down the equation on your green sheet, the area of a rectangle equation and the area of a triangle equation, if you didn't know them. When do I use that? When they give you a graph. This is the best definition of work today. It's called the work energy theorem. It's unfortunately also, no pun intended, Haley, the most amount of work, the most amount of writing. What is the work energy theorem? Work is the change in potential energy plus the change in kinetic energy. And if you want to, underneath the potential energy, you can put a subscripted G for gravity, like the MGH potential energy. Can you go see where that is on your formula sheet? I think I gave it to you. Yes, Roberto? Although, for some reason, I wrote kinetic first and then potential. Did I? I'm going to change that next year. And for some reason, I put it above the law of conservation. I'm making a mental note to change that next year, too. I don't know why I did that. May have been a formatting thing just to fit it all on one page. I can't remember. Okay. Work is the change in potential plus the change in kinetic. Oh, and Emily, what's change in anything? Top left corner of your formula sheet. Final minus initial, okay? So change in is final minus initial, and work, the work energy theorem, the equation that relates work to energy, is the change in potential plus the change in kinetic. And this is going to give us some actually cool applications. Example 1, a cyclist weighs 65 kilograms. Her bike weighs 7.2 kilograms. You know what? Let's combine that right now into one mass. On your calculator, can you go 65 plus 7.2? I think it's 72.2, but double check me. Yeah? If she's pedaling over level ground, we should underline the phrase level ground. That's going to become important, trust me. How much work does it take for her to increase her speed from rest? You know, another phrase I would underline is from rest to 5 meters per second. Kara, what's this question asking me to find after the comma? How much what? Say it, you're getting loud and proud? Okay. Don't write this down. Don't write this down. Don't write this down. My first thought, you said how much work? My first thought, my brain would think, well, work equals force times distance. Don't write that down. Is there, look at the question, is there a force in newtons in this question? Is there a distance in meters? And so I would hear the sound of a record needle getting dragged across the record. And in my brain, I would, nope. My next would be, well, maybe they gave me the area underneath a force versus displacement graph. Be stupid obvious. Kara, did they give me a graph in this question? No. So as a last resort, and this is what you can write down, I go to the work energy theorem. Work equals the change in potential plus the change in kinetic. From my formula sheet, Kara, what's the equation for potential energy, for gravitational potential energy? 3 letters. You'll find it in this unit. It'll say PE equals. It's okay. Haley, you want to give her a little pointer? Oh, you see it. What? Loud and proud. What? Okay. What 2 words did I underline in the first paragraph? Level ground. Is there a change in height in level ground at all? So, and I'm going to most of the time this year put it over level ground. I'll show you one where there isn't, but we can say that because of level ground. And Emily, what did you say change in anything was? What's my equation, Emily, for kinetic energy? This is going to end up becoming work equals a half mv final squared minus a half mv initial squared. There's my final minus initial. There's my final minus initial. Oh, Emily, from rest, what's VI as a number exactly? What's my initial kinetic energy as a number exactly? So we could get away with doing this, and now it's straight plug and chug. How much work? It's going to be 0.5 times 72.2 times 5. Don't forget the squared. That's how much energy this cyclist gave up from their body, food energy, to get the bike and them to this kinetic energy, to this speed. What do you get? And can you give me all of the sig figs? And Jordan, I'm looking for you to be typing on your calculator now. I think it's 900 something. 902.5? Sounds like a bad TV show. Jules. Wow, that joke skewed way too old. You don't remember 902.1, the Beverly Hills terrible show. Anyways. How many joules? 902.5. And I wrote all the sig figs because we're going to do a little comparison. B. Charlie, what's B asking me to find? How much work to increase from? By the way, from rest to 5 meters per second, how big an increase is that in meters per second in your head? From 5 to 10 meters per second, how big an increase is that? But you're not going to get the same answer. This is where, remember I told you a couple of weeks ago that squared dominates your life in ways you don't realize? Here it is. It wants us to find the work. You know what? It's not force times distance. It's going to be change in potential plus change. Oh, is it still level ground? Yeah, so I would still cross that out. It's going to be the work equals a half mv final squared minus a half mv initial squared. Also, I should point out, although there's an m in both of these terms, is there an m in work? It takes more energy to get heavier people to cycle faster. It's why if you're overweight, it's harder to get into shape because you are doing more work, burning more energy to try and get the same bang for your buck. Hey, let's crunch the numbers. So it's going to be 0.5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. And then once you've written that down, go to your calculator. Roto, what'd you get? I had somebody last class say, hey, Mr. Dueck, because of the squared and because now we're at 10, which is twice as fast, is that 4 times the energy? If you actually divide this number by this number, you'll get 3 because this is 1 times the energy plus 3 times the energy makes 4 times the energy if you started from rest. But we didn't start from rest this time. Somebody asked that. I just thought I'd point that out because some of you might have tried to divide. Ooh, Charlie, let's keep going. From what to what? You know what? You should be able to, on your calculator, just backspace and put a 15 squared there and a 10 squared there. I'll write out the numbers. But you might be able to get away without having to write anything down at all if you know how to use your calculator. If it's one that you're familiar with and you know how to use, you might know how to backspace and edit and save yourself some typing. I don't know what you'll get here. Valentin, what'd you get? 4512.5 joules. And again, 15 meters per second is 3 times faster. If you want to figure out where the 3 squared 9 comes from, if you divide this by your answer from A, you'll get 8 plus the 1 times, there's your 9. So already one cool application, we can start now to look at rocket science. Now in physics 12, we'll do proper rocket science. We can just do a model rocket right now, example 2. It says a model rocket reaches a height of 340 meters when launched. If the top speed of the rocket is 85 meters per second, how much work does the rocket engine do on the rocket? Haley, what's this question asking me to find? How much what? Don't write this down, don't write this down, don't write this down. My first thought would be that. Now, don't write that down. They gave me a kind of those meters, distance, and you could say, well, maybe the force is mg because it's vertical, but I'm noticing there's this 85 that I haven't used yet. And that's really my only hint that this is what you can write down. I'm going to use the work energy theorem, change in potential plus change in kinetic. Emily, what's changing? Anything? That's probably going to be your line. Final minus initial. And this time, Haley, you agree there is a change in height, so none of these are necessarily going to all cancel out. Let's spread them out. Ooh, what's my equation for gravitational potential energy, Kara? 3 letters? Okay, so let's go like this. It's going to be mgh final minus mgh initial. There's, Emily, the final minus initial for the delta PE, plus a half mv final squared minus a half mv initial squared. And you'll notice, Violet, the m's don't cancel. There's no m in work. It takes more money, more fuel to put heavier things in orbit. NASA is willing to spend a lot of money to reduce the mass. I think right now we're at about $15,000 a pound to put something into low Earth orbit, so it's worth spending a couple of $100,000 to shave off 50 pounds. You'll still come out ahead. Oh, are any of these zero? Potential energy will be zero when we're on the ground. Where do all rockets start out? Okay, so Haley, you agree with me? Yes? And you've seen a rocket launch on TV, or you've seen one in the movies. Before they press the launch button, how fast is the rocket traveling? Be stupid obvious. Right? So for this model rocket, what we're actually finding is how much energy needs to be stored in the rocket engine. How much of the rocket, it's a powder, I can't call it gunpowder, it's something else, but how much of the chemical energy do we need to have if we want this model rocket with this mass to reach a height of 340 meters and a top speed of 85? Let's crunch the numbers. 0.15 times 9.8 times 85. That's how much energy we need to get it to the height, but it needs to be moving to get there. Don't forget the squared. Oh, hang on. 85 is wrong, Mr. Dueck. Sorry, I did 85. The height is 340, isn't it? I'm so sorry, folks. Sorry, YouTube. I never make mistakes. Funny joke. I'm putting this one on YouTube, warts and all. I make mistakes, they go on YouTube still. So, is that okay? MGH and a half MV squared. I don't know what you're going to get here. Thank you, Charlie, for picking up the hint. Thank you, Valentin, for picking up the hint. Mia, what'd you get? 104. Okay. Is there a part B to this question? I'm going to round off now. I'm just going to say 1,040 joules, a little more, but I'll go to 3 sig figs, 1,040 joules. We're going to revisit this properly in Physics 12 because this is how you figure out how much rocket fuel to put something into orbit. The problem, Florin, is you can't use MGH because G is not 9.8 as you get further from Earth. So what we'll actually have here is an equation that measures how far you are from the center of the Earth. And it's a complicated question. It ends up, Charlie, being about 12 lines long. It takes an entire page. It's rocket science, what are you expecting? But it's cool. You can actually figure out this is how much rocket fuel, and if you knew how many joules per liter, you can actually calculate how many liters of rocket fuel you need to put something into whatever orbit that you want. Example 3. Example 3. A 1,250 kilogram car is traveling at 35 meters per second over level ground. You know what? Level ground is something important to notice. Tyson, now that you're done yawning, what's A asking me to find? Work, you say. Oh, to bring it to a? I would probably mentally catch that because in case I need it, what's VF exactly as a number? Okay, I got that in my back pocket if I need it. So work, my first thought, don't write this down. Did they give you a force in this question, Tyson? Did they give you a distance in this question? Nope. Then my next thought would be, hey, maybe it's the area underneath a force versus distance graph. Did they give me a graph? You know what? Work energy theorem, but it's always my last resort. Change in potential plus change in kinetic energies. Oh, what two words did I underline? So what's my change in potential energy? Now, by the way, if there was a change in height, it's not that hard to work it in. You just measure the elevation change if you're on a hill, and you can work it in easy peasy. So it's really not that much more difficult. But yeah. Emily, what's change in anything? So it's going to be a half mv final squared minus a half mv initial squared. There's my final minus initial. Oh, Tyson, what did you say the final kinetic energy was? We're going to get a negative answer. See the minus sign that's still kicking around? That's going to make our answer negative. That's okay. What this is telling me is this car has to lose energy if it's going to stop. Yeah. So let's crunch the numbers. It's going to be negative 0.5, 1250 times 35. Don't forget the squared. This car's got a fair bit of energy. And 35 meters per second, that's about 110 kilometers per hour. So this is coming to a stop on the freeway. You got to lose a fair bit of energy. It's going to be negative because you're losing energy. Violet, what'd you get? I think it starts with a 7. That's in the 700,000s, I think. Joules. B. B. By the way, where does that energy go? It's got to go somewhere. That's what the law of conservation of energy sheet says. Where does it go? Heating up your brakes, yeah. Oh, unless you have an electric vehicle. Anybody here have an electric vehicle? So the regenerative braking system bleeds that off to the battery. Not all of it. It's not perfect. But one of the reasons electric vehicles are so efficient, you take your foot off they don't call it a gas. I took a Tesla for a test drive a few years ago, and the salesman said, we call it a go pedal, not a gas pedal, no gas. So, okay, when you take your foot off of the go pedal, it feels like you're hitting the brakes, even though you're not. It's bleeding this energy back into the battery. Oh, it also means you don't hit the brakes as often. Your brake pads last way longer. So there's some neat stuff going on here. Michaela, let's read along. Let's do B together. It says if it takes 82 meters to come to a stop, what force is required? Michaela, what's B asking me to find? What? Okay, don't write this down. I mean, my first thought might be this is a job for a free body. Wait a minute. What did I find in part A? Okay, and what's this 82 a measure of? What are the units next to it? Which is a measure of what? Starts with letter D. There isn't by chance a version of work that has a distance in it too, is there? Go look at your formula sheet. What's the first equation for work? What times distance? See where we're going? So now we can go like this. Work equals force times distance. Because I can use my answer from part A, Michaela, get the F by itself. By the way, which force? Friction, if it's an internal combustion car. Get the F by itself. How to move the D over? Or as we like to say, divide. But you're correct. It's going to be work divided by distance. It's going to be your answer button divided by 82. You're going to get a negative answer. This negative, because force is a scalar, is telling you a direction. Michaela, if the car is going forward, which way must the force be pointing to bring it to a stop? Be stupid obvious. That's what the negative here. Now the negative is telling me a direction. This won't work out evenly, but store it on your calculator. What do you get? Give me the 3 sig figs. 9. So I'm going to go negative 9,340 newtons, but I'm going to store it on my calculator. Okay. And then it says, what is creating the force? I'm just going to draw an arrow up here, and I'm going to make a little note, friction. And where is this energy going? Heat. Ooh, Jordan, what's C asking me to find? I only have one equation that has a mu, a coefficient of friction in it. Which one? We're brushing the cobwebs off. We're doing some review. Let's write that down. Friction equals mu times the normal force. Jordan, let's get the mu by itself. How would I get the mu by itself? Put it on the bottom. Yeah, we're going to divide it. I agree. Mu is going to be friction divided by the normal force. In fact, the coefficient of friction is going to be, now I'm going to ignore the negative because the coefficient of friction is a scalar. You'll have a negative sitting on your calculator. Just ignore it. Divided by, I don't know the normal force. You know what this is a good job for? Hey, let's over here. What are the forces acting on this car? Get the obvious one. Good. Is the car sinking into the ground like quick? Is it flying like Superman? So there's going to be a normal force, same size, pointing up. What else? Which way? Yeah, and remember, this bugged you because people were saying, Mr. Dueck, the car is still moving forward. Doesn't there have to, it's backwards, slowing it down if the car is moving forward. How can it be moving forward with no arrows pointing forward? It's slowing down. Newton's laws tell us acceleration, not velocity. That's the free body diagram for a car hitting the brakes. And by the way, the free body diagram for a car speeding up was friction pointing forward. That's why cars can't drive on ice, no friction. Okay, I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. So go answer button divided by mg. In brackets, Kara, on yours, because you don't have a fraction button. Ignore the negative. One of the few times you'll tell me to do, you hear me say that. I was trying to make up good numbers, I think. I hope we have something reasonable. Destiny, what'd you get? 6.2 or 6.3? 6.2? Units. It would be newtons divided by newtons. The units cancel. So where might you use this? If you're a tire manufacturer and you know the specifications and speed limit of a certain car and how much distance it has to stop on a certain road, you would say, this is how grippy I need to make my tires. It's a little more complicated than that, but this is where you would start to use that. And now I fulfill a promise from several months ago. I like example 4, I like example 4, example 4 is our next question. Example 4 says this. An RCMP officer is investigating an accident. A car has struck a pedestrian at a school crosswalk. There are no witnesses. The officer measures the coefficient of friction at the accident site to be 0.65, and he measures skid marks that are 49 meters long should the RCMP press charges against the driver. You might recall way back in November, I gave you an RCMP question where I had the cell phone pick up the sound of the skid marks so we knew how long they were skidding for, and we calculated the final speed, and I said, should they press charges? And you all said no. And then I said units, and you all, that's meters per second. You convert it to kilometers per hour. You, holy smokes! Yeah, we're pressing charges. Remember that question I did way back in November? But I had to have, Jordan, the stupid fluke of the cell phone picking up the sound of the skid, which never happened to me. But I promised you then, once you learn more physics, you can do it straight from the skid marks. So here it is, as promised. What are we trying to find here? What's going to allow us to determine whether we're pressing charges or not? I mean, it's a hit and run, so no matter what, we're pressing some charges, but can we include speeding through a school zone? What are we trying to find here? Which one? Initial or final? Because what's the final velocity of every car accident ever? Okay, let's make a little note here. We want to find this. Now, the next bit is not immediately intuitive. I'm going to write the most obvious statement ever. Work equals work. That has to be correct. Write that down. On the left-hand side, I'm going to do Michaela's version of work. Michaela, what was the equation for work that you read us? Because I have the skid mark distance. That was my hint to do that. And on the right-hand side, since you said we want to find V, I'm going to go change in potential plus change in kinetic, because the kinetic has a V in it. The only thing I need to retype this question, I should have said over level ground. We're going to assume level ground, but in real life, by the way, if there's a hill involved in the accident, you can just measure the change in elevation, and it's not that hard to work that into your calculations. Emily, what's change in anything? Okay, so on the right-hand side, we're going to end up with a half mv final squared minus a half m V initial squared. Nolan, what did you say V final was? And so this term is going to vanish. In fact, the right-hand side is going to be negative. What we should do is we should have put a negative here because that force is in the opposite direction of the motion. There's an implied negative there. Which force? What's the force that brings the car to a stop, folks? So let's also put a little friction right there. And then on the next line, we're going to write, ooh, Jordan, what was the equation for the force of friction? On the next line, I'm going to say the negative is dropping down, and then I'm going to quit writing the negative because they're going to cancel out. But it's mu times the normal force times distance. Jordan, see there's a negative here and a negative here. The negative divided by negative is going to be, they're going to cancel. Okay. On the right side, I'm going to drop this down and write it as mv squared over 2 because I want to get the v by itself, and that's cleaner. On the left side, oh, I don't know the normal force, but I think it's the same free body diagram. So look. I don't know the force the same size as the normal force. Okay. So I get mu mg, and then the d drops down. And ooh, Vienna, there's something kind of cool here. Is there an m in the right-hand term? Is there an m in the left-hand term? Can the RCMP start their investigation even if they don't know what car was involved? Yes, they can. And in real life, if someone was killed horribly, there'd be paint flecks in the body, sadly. And so they would take paint fleck samples. They would start going to body shops, auto shops, finding anybody that needs repair. They'd be looking for any cars that had unexplained dents. About 7 years ago, my best friend was hit by a hit and run in Abbotsford. Person took off. And it was a police officer living next door, noticed their neighbor has a really weird dent on the front, and this police officer knew enough to know. That's pretty much what a human being does when you get hit by the bumper. So he called it in to his friends on the police department. She never got charged because couldn't prove she was driving. It's really tough to get hit and runs without witnesses because all they need to say, I wasn't driving, prove it. And if there's more than one person living at the house, you can't prove who the driver was, and you can't arrest everybody because maybe someone wasn't the driver. Just saying. But here, you can certainly start the investigation if you've been on the car. Nathan, get the v by itself. How will I move the 2 over? How will I get rid of the squared? I suspect this is an equation that an RCMP crash investigator has memorized the same way you've memorized the 9.8. Your initial speed is the square root of 2 mu g d. Square root. It's going to be the square root of 2 What's mu, Nathan? I don't know what's mu with you. Oh, and they have a machine. They have a little thing they drag behind them, and that's what measures the coefficient of friction. It's kind of a neat little device. I've seen it. What's the coefficient? 0.65? G, 9.8. And what was the distance? What do you get? I think it almost works out evenly to 25, right? It's like 24.99 or 98. That's a fluke. I didn't plan that. So let's say 25 meters per second. And do me a favor, with your answer button, convert that to kilometers per hour. It's something to do with a 3.6. How fast were they going in a school zone? You could certainly add speeding in a school zone. You could probably add reckless driving. Oh, why is this the minimum speed? Why could they have been going faster? Be obvious. Don't look at the physics. Look at how we figured out the speed. What did we measure? How could they have been going faster? They might have slowed down before skidding. You don't skid every time you hit the brakes. They might have lost some of their speed before skidding, right? So you could certainly make an argument. Now, if you want to be really nitpicky, and again, this is terrible, but the person's body would have absorbed some kinetic energy, and you might have to factor that into your calculations as well. But yeah. So cool application. Wish we didn't have to, but a cool application. 2 more, we're done. Oh, yeah. You've had YouTube all of your lives. YouTube came on at about 2006. In 2007, a motorcycle driver from Vancouver Island posted this, I'll call it a dash cam video, even though motorcycle doesn't have a dashboard, and it went viral. And he was stupid because the RCMP tracked him down and impounded his motorcycle. This is what he posted. Put your pencils down and look up. It's from 07, so the resolution is lousy, but you can see the speedometer, which was important for the physics. Why are we seeing the sky? How fast are we going? Units? Look at the inside speedometer closely. Units? This is miles per hour. 220 miles per hour. Convert 220 miles per hour to meters per second. 98.4. You know what? Let's write down VI equals 100. Because I think he's actually going a little faster. He's pinned the speedometer. So can you write down next to this question, VI equals 100 meters per second? By the way, that's a football field every second. VF is 100 miles per hour. Convert 100 miles per hour to meters per second. Siri says 44.7. Call it 45. Let VF be 45 meters per second. All right. So VI was 100. Is that what I said? Jeez. VF is 45. This became viral for the time, news, like it made the news. And I recall they said what bike it was because the RCMP impounded the bike. I looked it up years ago when I got the specs. Then I made an estimate as to the mass of the rider. And so I said, I think the total mass was about 300 kilograms. I'm going to make a bit of a guess. But okay, let's dive into this. Nolan, what's A asking me to find? Just read it to me. What I'm going to find is the work done by friction. I'm going to use the work energy theorem. Work equals the change in potential plus the change in kinetic. You all saw the video. Did that road look like it had hills? So I think we can safely say no change in potential energy. Emily, change in. So this is going to end up being a half mv final squared minus a half mv initial squared. No, it's going to be a negative number because he is losing energy. It's going into heat. Let's crunch the numbers. It's going to be 0.5 times 300 times 45 squared minus 0.5 times 300 times 100 squared. It's going to be a big number. How much energy was lost to heat and sound, but we'll call it heat. Michaela, what'd you get? Oh, you're sneezing. Sorry, my bad. I think you get over 1 million, if I recall. 1196. Yeah, almost 1.2 million joules of energy. And again, this is why I keep saying, Haley, one of the big bonuses with electric cars, you can capture a lot of that. A friend of mine has a Chevy Bolt, and so his daughter lives in Kamloops, and he takes the Coquihalla to go visit her. And then he says he makes the top of the Coquihalla, the summit, with a nearly dead battery. Coming home, at the bottom, he's fully charged. He gained all that energy back. It may as well. So electric vehicles, the future. Because of regenerative braking. He's just letting the potential energy get turned into kinetic, regenerating his brakes. B, where did that energy go? What have I been saying? Where is that most of that energy wasted to? Yeah, heat. C. Okay. Destiny, what's C want me to find? Ooh, what's our power equation from our formula sheet? Oh, it's going to be negative. We'll ignore the negative now. The power, we'll just call it positive. The negative is just saying it's an energy loss. It's going to be your answer button divided by, we need the time. Okay. So we're going to look at the timestamp of the video. Let me cue it forward a little bit. About to here. We'll look for right when we hear the sound of the engine change, and then we'll look for when he gets to 100. Okay, I see 50 seconds. Let's just remember 50. .107, so 50 to 1 minute, 17 seconds. Okay, I got a time. Up here where we have our data, let's list t equals 17 seconds. Okay. So answer button, ignore the negative, divided by 17. How much power? Also going to be a pretty big number. Destiny, what'd you get? 7036. So I'll go 70368. Is that right, folks? Power's measured in watt. And then just for giggles, Violet, what does D want me to figure out? Take your answer button and divide it by 60. How many light bulbs could we have lit with this? Sorry, how many? Wasted energy. One more, we're done. Oh, he's burning a lot of fuel. Yeah. The very last example of the course, Mr. Dash. Gonna get all emotional. Okay, here we go. Another cool application, we can look at rocket cars. So a rocket car is initially at rest. You know what? At rest is always important. I'll make a mental note. And it's on a horizontal surface, which means level ground. The engine is ignited, and this graph shows the thrust force versus the distance traveled. Okay. A says, why do you think the force decreases after 15 meters? Why do you think here suddenly the force starts getting smaller and smaller? This is not physics, this is how rockets work. What do you think is going on right there? Why is the force getting less and less? No, then how do rockets work? What happens near the end of the rocket? It's losing fuel. Yeah. Okay. Because here, after 25 meters, no force. Now it's just going to be going at a constant speed if they ask that. Okay. Tyson, what does B want me to find? This is not an intuitive question. This is a fairly tough question. I might give you one of these on your quiz. I don't think I'm going to give you one of these on your test, but it's a cool application. What's it asking us to find? I have a force versus distance graph. You know what? This area is going to be the work. So I'm going to write this. Work equals work. I've done that once before, I think. Except, Haley, on the left, I'm going to say, I'm going to use the area definition of work. And on the right, I'm going to use today's work energy theorem, Roberto. Change in potential plus change in kinetic. What did I say the word horizontal meant? Gone. Emily, what's changing anything? So on the right-hand side, it's going to be a half mv final squared minus a half mv initial squared. Oh, what two words did we underline? So, gone. On the left-hand side, what shape is this? And I hope you did put I told you, if you don't know, you better put the formula for the area of a rectangle and the area of a triangle on your formula sheet. If you didn't do that, you want to do that. I said put it right next to this unit, to the work energy section. So what's the formula for the area of a rectangle? What's the base? What's the height? Okay, so here on the left, let's go 15 times 160. Let's crunch that. Turn that into a number. 2,400. And on the right, because I want to get the v by itself, now I'm going to write it as mv squared over 2. Tyson, how will I get the v by itself? How will I move the m over? How will I move the 2 over? How do I get rid of the squared? So if I hear you're telling me the speed is going to be square root 2 times 2,400 divided by 5.2. Yep. Now, Jordan, I should point out, in real life, if you're getting a thrust vector graph, like for a rocket engine, it's often curvy and you need calculus to find the areas. I simplified it, but the principle is still the same. What'd you get, Jordan? 30.4, rounded off properly? And that's going to be meters per second. C says, find the speed of the car after 25 meters. Okay. It's going to be the same thing, except after 25 meters, Kara, I need to include this area as well. In fact, Michaela, I'm going to argue for C, I would start out work equals work. I would say the area is going to be the change in potential plus a change in kinetic. I would say we're still on horizontal. Emily would say change in anything is final minus. We're still starting from rest. You know what I'm going to do? I'm going to say I think it's still going to be on the right-hand side. It's going to be mv squared over 2. On the left-hand side, it's going to be 2400 plus the triangle area. Jordan, what's the equation for the area of a triangle? It's going to be base times height divided by 2. What's the base of that triangle? How long? 10. What's the height of that triangle? So that's a 10. That's a 160. Can you go 2,400 plus 10 times 160 divided by 2, please? I think 3,200? Double check me. No, yeah. What'd you get, Nolan? I know. Get your calculator out. Is it 3,200? That equals mv squared over 2. You know what, Tyson? It's going to be the same we just did, except instead of a 2,400 right here, what number is going to be sitting there? You might be able to backspace and edit. If you have a good calculator that you know how to use well, you might be able to save yourself some time and backspace and edit and not have to retype this from scratch. It's going to be the square root of 2 times 3,200 divided by 5.2. Should be a little faster, but not by much, because the force is getting weaker and weaker and weaker. Point